Let's continue our discussion about the acid-base properties of the carbonyl group, focusing now on the alpha carbon and in particular the hydrogen atom attached to that position. If the alpha carbon is sp3 hybridized, then it's possible for a base to come in and deprotonate that hydrogen. This proton transfer step produces the carbanion that's shown here. This carbanion is resonance stabilized by N to pi star pi type interactions to make the structure that's shown here, which we commonly refer to as the enolate anion. In order to see the importance of this carbonyl group and stability of the anion, let's take a look at the closely related structure that's shown here. Now the alpha carbon, with its hydrogen atom, sp3 hybridized, is flanked by two carbonyl groups. And so when a base comes in to remove that proton, the proton transfer step creates a carbanion that has resonance stability from N to pi star pi type interactions to produce this oxygen anion, and that structure can turn around and donate that pair of electrons into the other oxygen atom so that both oxygens are sharing the negative charge along with that alpha carbon. Because of this greater delocalization, B, the anion shown here, is more stable than A. And now we can understand the acidity of the alpha hydrogen for these two examples and the importance of that resonance stabilization by the carbonyl group. We'll do that by making a plot of free energy versus reaction progress or species in equilibrium. We'll put the neutral compounds on an equivalent position because most of the energy, as we know, is associated with the negative charged species, and so the neutrals we'll put at an equivalent energy. Now we've just seen how B is more stable than A, so on this diagram it should be obvious that the equilibrium will be more favored to the right for the structure which has two carbonyls versus the one that has a single carbonyl. In other words, we conclude that this is the weaker acid, it's less prone to give up its proton, this is the stronger acid. We can look at an entire series of these kinds of compounds where I've highlighted for you the alpha hydrogen, and you can see that the pKa's range from something that's relatively weak acids to rather strong acids when we begin to get several of these adjacent carbonyl groups or other electron withdrawing groups like the nitro group, for example, or the nitrile group that's shown up here. In general, this trend can be understood simply by considering anion stability through delocalization.